I hope that all of you had as much fun as I did working your way through the Magic School Bus adventure and beginning to iteratively draw your glycolytic pathway depiction. Probably at this point it is imperfect but beautiful, and with time you will build it into the final depiction that you're happy with. So I want to draw your attention to the steps in glycolysis that are metabolically irreversible. So recall that we drew our attention to steps 1, 3, and 10 as those very important points of regulation. I'm just going to take a moment to call your attention to those steps. The first catalyzed by hexokinase, step 1. Then the third step catalyzed by our ever famous favorite PFK1, so step 3. And then finally step 10 catalyzed by pyruvate kinase, being the third of our metabolically irreversible steps in the Ebden-Meyerhof pathway. Now, all of these are epically important points of regulation, and I'd like to talk a bit about each one of those, beginning with hexokinase. So hexokinase is actually quite a complex enzyme because in the tissues of the body, it exists as multiple isozymes. So in fact, there are 4 isozymes of hexokinase. And most of those isozymes, at least isozymes 1 through 3, are feedback inhibited by product. So glucose 6-phosphate is a feedback inhibitor of hexokinase, so negatively down-regulating that enzyme. So isozymes 1 through 3 are feedback inhibited by glucose 6-phosphate. So I'll just say G6P down-regulates. However, there is a 4th isozyme specific to the liver. This liver isozyme is called glucokinase. Glucokinase is unique for a number of reasons. It is not feedback inhibited by glucose 6-phosphate. It is also unique in that while the other isozymes follow Michaelis-Menten kinetics, we see glucokinase showing a sigmoidal curve and failing to follow Michaelis-Menten kinetics. So glucokinase, if we are to draw our ever enjoyable curve showing initial velocity as a function of substrate concentration, we would recognize the isozymes 1 through 3 as displaying Michaelis-Menten kinetics and having a very low Km, so approximately 0.1 millimolar, so just is extremely low Km where you hit, that's not quite half maximal, but there we go, somewhere around half maximal, that their Km is very low. So let me see here. Kms of approximately 0.1 millimolar. But when you start to think about glucokinase, this specific liver isozyme, it actually has a slightly sigmoidal curve, and it has a Km of somewhere around 2 to 5 millimolar. So it's just a much higher Km value. So really not to scale here in my simple drawing, but this would be Km values that are much higher, 2 to 5 millimolar. And so what that means is that this isozyme is quite literally regulated by availability of substrate. So glucokinase is only turned on after a meal. So after you've eaten your dozen Krispy Kreme donuts and the glucose concentrations are extremely high, like maybe somewhere between 5 and 10 millimolar post-meal, that's when glucokinase is really going to get kicking and get going. And when you think about that, this makes sense within the context of the liver, because the liver is the site at which glucose is stored as glycogen. And that happens to a less appreciable extent in some other tissues, such as your slow twitch muscle tissues. But this isozyme will really be upregulated only at high blood glucose, saying, hey, store away this excess glucose as glycogen. So where isozyme 1, for example, is really quite specific to being a glycolytic enzyme, that the goal of that isozyme is to create glucose 6-phosphate to go on to the rest of the steps of glycolysis. Glucokinase is there to create glucose 6-phosphate so that glucose 6-phosphate can get utilized to build glycogen and store away for a rainy day within the liver. So a different function of that glucokinase enzyme, and so its regulation fits that function, and that regulation takes place through the Km value. So glucokinase is a heavily regulated enzyme, and some sort of unique regulation that's taking place there. So glucokinase is not inhibited by glucose 6-phosphate, so that, of course, a liver can convert glucose to glucose 6-phosphate and then to glycogen when the blood glucose concentration is high. And glycolysis is not the goal. It's not the name of the game. It's storage as glycogen. Excellent. Let's take a look at PFK1. The regulation of PFK1 is absolutely epic. So PFK1 is allosterically regulated by ATP. We would see that as being likely. We know that the final eventual product of glycolysis of the Embden-Meyerhof pathway is ATP. So ATP is a negative regulator of PFK1. Additionally, we already knew this. Earlier we did that exercise where you looked at ADP as an allosteric upregulator of PFK1, but also AMP. So remember, AMP and ADP indicate need for ATP. So they're like saying, hey, get your butt moving. We need more ATP. They are reciprocally regulated within the nucleoside pool. So if there's low ATP, high ADP, and AMP tell PFK to get going and making more ATP. Things get a little bit more complicated with this next line of regulation, because another feedback inhibitor of PFK1 is citrate. So citrate feedback inhibits, but you may be thinking, I'm not even sure where citrate comes in. I don't remember it being a product of the Embden-Meyerhof pathway. It is not. So here we have to think all the way to the TCA cycle, where it is the first intermediate of the TCA cycle. So this is like way epic, far down the road feedback inhibition. This is really important because if the energy needed by a cell is coming primarily from fat, breakdown, then citrate will be high and it will tell the glycolytic pathway to stop breaking down carbs. Basically, it's saying, hey, we're getting enough energy from fat. Stop breaking down these valuable carbs. And so citrate is really going to feedback inhibit, allowing the recognition that the energy needed is coming from fat breakdown. Additionally, we also see hydrogen ions, so excessive acidosis, like excessive hydrogen ions, will downregulate PFK1. This is when we're talking about excessive fermentation, lactic acid fermentation, where protons are being generated so rapidly that it's within the best interest of a cell to downregulate that energy generation and say, whoa, we are hitting acidosis. This is not a good thing. So these are some ways that PFK1 is regulated. And right now you might be thinking, oh, all of these kind of make sense, but in fact, things become much more complicated with PFK1. So let's move our way to a different depiction and take a look at that one more layer of complex regulation. Sometimes I feel like I'm like in Star Wars when I'm saying, there is another epically important regulator. So let's take a look at that.
Fructose 2,6-bisphosphate. It is an activator of glycolysis in mammalian cells, in fungi, and in plants. Very important regulator in those systems. And you probably are looking at it and saying, yeah, but Rachel, I don't even know what it is. And that's probably true, and so that's why I'm going to explain where it comes along here. So try to stay with me. This is complicated. Let's begin by pointing out where we are here. This is glycolysis, okay? So recognize that this is step 1 of glycolysis right here, where glucose is phosphorylated. That's step 1. This is 2, the rearrangement, where glucose 6-phosphate is converted to fructose 6-phosphate. This is the ever famous step 3. That's catalyzed by PFK1, and then from here on down there's step 4, and of course 5 would be the interconversion between these two trioses, okay? So this is glycolysis that's happening on the far left. Now what we notice is that this third intermediate, if you will, of glycolysis, fructose 6-phosphate, is going to be one of those sexy molecules that we talked about that is actually recognized and acted upon by more than one enzyme. So that's why it's important when we talk about phosphofructose kinase to call it PFK1, because there's 2 types of phosphofructokinase. There's PFK1, and fructose 6-phosphate is recognized by a second PFK enzyme, PFK2. So fructose 6-phosphate can not only get converted to fructose 1,6-bisphosphate, but it can also get converted to fructose 2,6-bisphosphate. So there's an alternative, if you will, pathway that can occur, or an alternative branch that can occur for fructose 6-phosphate, converting it into a different product besides fructose 1,6-bisphosphate. So PFK2 is a kinase, as we recognize. It does transfer a phosphoryl group from ATP to make doubly phosphorylated fructose molecule, and this is the regulator, okay? So fructose 2,6-bisphosphate is the feed-forward activator of PFK1. Weird. Think about this. The product of the reaction catalyzed by PFK2 is the feed-forward activator of PFK1. Wrap your mind around that one. Now hang on. PFK2 allows for more regulation to be enacted here. Remember how we talked about how sometimes these enzymes can be regulated in multiple ways, and they are indeed here stimulated by inorganic phosphate and inhibited by citrate. So inorganic phosphate, right, think about that. Let's think this through. Inorganic phosphate would be high when ATP is low. So inorganic phosphate would say, whoa, we need more ATP, so it would encourage the formation of fructose 2,6-bisphosphate, which would then feed forward activate PFK1, which would then upregulate glycolysis, which would lead to more ATP, right? Okay, now citrate. Citrate says, whoa, hold on, feedback inhibits, right? It says slow down glycolysis. So it's going to inhibit PFK2, lowering the concentration of fructose 2,6-bisphosphate, slowing the upregulation or feed-forward activation of PFK, slowing glycolysis and lowering the amount of ATP produced. Okay, that makes sense, doesn't it, once you think through everything. Now, fructose 2,6-bisphosphate can be further acted on by another portion, another activity of the same enzyme, the phosphatase activity. So PFK2 is a multifaceted enzyme. It has more than one activity. It's got a kinase activity and it's got a phosphatase activity. So the phosphatase activity can act on fructose 2,6-bisphosphate to cleave off the phosphoryl group and convert it back to fructose 6-phosphate. Okay, that would be under conditions where this upregulation was no longer needed. Okay, now it makes sense that fructose 6-phosphate itself will actually inhibit the bisphosphatase activity of PFK2. Now let's think that through. If there's a lot of fructose 6-phosphate, then it would be desirable to feed forward activate PFK1. So it would be then desirable to downregulate the bisphosphatase, which cleaves the phosphoryl group off of fructose 2,6-bisphosphate, because lots of fructose 6-phosphate indicates, hey, we need to upregulate and feed forward activate this pathway because this is accumulating. So elaborate feed forward activation going on there. Wow, this is one of the most difficult concepts that we will cover. So it's important to go back to this one and make sure you understand it. Make sure you understand what conditions would lead to an increase in fructose 2,6-bisphosphate and what an increase in fructose 2,6-bisphosphate would cause in the glycolytic pathway, right? It's always a feed-forward activator of that pathway. Now before we leave this screen, I just want to explain a little bit about what we're going to write down on the next screen, because not only do we see this sort of local regulation of feedback inhibition and feed-forward activation, there's also a lot of global regulation that's going on within metabolism as well. So, for example, when you think about the hormone glucagon, remember glucagon signals hungry. So glucagon is going to primarily target the liver, and it's going to say to the liver, whoa, we need some glucose to the vital tissues right now. We need glucose to be released from the liver and to be given to things like the brain in order to fuel function. And so at that point, glucagon is going to signal a major downregulation of glycolysis within the liver, saying, hey, whoa, stop using the sugar here, start synthesizing sugar, reverse your engine, start making sugar, stop using it in glycolysis. So glucagon is going to be a downregulator of glycolysis. Let's talk about how it does that. Glucagon actually is going to target specifically PFK2. Glucagon signals the adenylyl cyclase signaling cascade that we talked about before, and in that signaling cascade, one of the targets for phosphorylation is actually this enzyme PFK2. And so when glucagon is high, PFK2 actually will get phosphorylated, and that will decrease the activity of PFK2 kinase, so it will downregulate that PFK2 kinase, and it will actually upregulate the phosphatase. So what that means is that that will lower the concentration of fructose 2,6-bisphosphate, which will slow the upregulation on PFK1, which will ultimately slow glycolysis. So that's a good thing, right? It slows glycolysis, saying we need the sugar elsewhere, stop using it here. So this is an important function of glucagon. So on a more global level, the way that it's signaling the liver in its entirety, saying, you know, save sugar for the rest of the important organs.
finally, let's take a look at step 10, the pyruvate kinase catalyzed step, and the final metabolically irreversible step of the Epstein-Meyerhof pathway. Remember fructose 1,6-bisphosphate? Fructose 1,6-bisphosphate was the product of the first committed step of glycolysis. And fructose 1,6-bisphosphate is going to be a feed-forward activator of pyruvate kinase. So it upregulates the activity of pyruvate kinase. Additionally, there are some feedback inhibitors of pyruvate kinase, and you won't be surprised to know that ATP, the product, one of the epically important products of glycolysis, is a feedback inhibitor, saying, okay, there's enough ATP made, feedback inhibit. It's also very important to note that like the phosphofructokinase 1, as we looked at its regulation, glucagon and the levels of glucagon also matter here. So if we are way outside of our cell where glucagon is binding this liver hepatocyte, remember that it's going to trigger the adenylyl cyclase signaling cascade. So we have our receptor, we have our transducer in the form of a G protein, and remember G alpha heads on over to the adenylate cyclase enzyme. We get the production of cyclic AMP. We get the activation of protein kinase A. And then, so one of the phosphorylation targets is, in fact, pyruvate kinase. So when pyruvate kinase gets phosphorylated, covalently modified, we recognize that that shuts it down. So that phosphorylation slows glycolysis and triggers the bypass reactions of the reverse pathway called gluconeogenesis, by which pyruvate is used to synthesize glucose. So it's glucagon is saying, hey, we're hungry. Stop breaking down glucose, start making glucose, start shipping that glucose to very important tissues such as the brain. So triggering the liver to reverse engines. We need food. So that's another layer of regulation. So we get the understanding then of these regulations that take place at the 3 metabolically irreversible steps of the Epstein-Meyerhof pathway. And in class, we're going to add to our ever-evolving depiction of metabolism and show those regulation steps. And we're also going to think deeply about some thought-provoking questions.
So as we've talked about glycolysis, we've focused mainly in on glucose and the metabolism of glucose. However, we have noted at times that there are other sugars that can enter into the pathways, such as galactose, mannose, and fructose, and can be degraded for energy as well. However, there is a kind of interesting and fun side note that I want to talk about. This is something that I like to term the HFCS problem. HFCS stands for high fructose corn syrup, and rarely can you find anything in the grocery store, if you look hard, that doesn't contain some derivative of corn syrup in some form, most of them high fructose corn syrup. Fructose, where does it enter? Well, let's look at all of these. We've got a few sugars. Notice galactose, when it enters into catabolism, converted first to galactose 1-phosphate, then to glucose 1-phosphate, which is then converted to glucose 6-phosphate. So the same first, so if you will, enters in at the first intermediate that would be formed from glucose, so enters in at that point. Mannose converted to mannose 6-phosphate, which is then converted to fructose 6-phosphate, which is just the next intermediate down. However, when fructose enters into catabolism, it can be converted first to fructose 1-phosphate, which can then be cleaved down immediately to dihydroxyacetone phosphate and glyceraldehyde, which can be phosphorylated to give glyceraldehyde 3-phosphate. Notice, recognize these as occurring way further down in the pathway. In in fact, after step 4, where the cleavage has occurred. So what we see is that when fructose enters into catabolism, it bypasses that important step number 3 that's catalyzed by our favorite enzyme PFK. And so this can cause a problem, you betcha, because notice that the regulation, most of the regulation of glycolysis is enacted right there at step number 3. So fructose enters in and bypasses that regulation, which means that you get an accumulation of the product of glycolysis, pyruvate, which then you may get an accumulation of the next step in the transition step of acetyl-CoA. And acetyl-CoA, remember, is the precursor to the synthesis of fats and cholesterol. So there may be an increase then in synthesis of fats and cholesterol, which can lead to a condition called a fatty liver. Check it out. Amazing stuff.